Okay, a couple announcements. Our first exam is a week from tomorrow. It's going to be the same procedure as the pretest. We will have another written homework due a week from today, and that will conclude the material that's on that test. Okay, so what you turn it with this last homework, actually I have posted it already. This is the last homework for material on the exam. Everything we've done so far is covered. I will be giving you several things to help you prepare for the exam. They're not up yet, but there's a review outline. There's going to be another online system of practice problems called WebWork. We're going to use that. I'll give you some sample items so you just get to know kind of what the test is like, the feel of the test. Lots of multiple choice, but still invoking you to think, okay? So it's not just simple calculations and pick the right answer. It's not like that. It's based on all the understanding and ideas and concepts that we've been working on, okay? So there will be a section over here, exam prep, which I think is empty right now, but in the next day or two, I will put up an exam 1 folder that will have help for your studying, okay? There is a readings and workbook for Friday. That's posted. And like I said, next Wednesday's homework is posted as well. But for today, the one you're handing in today, so let's get your folding right, your heading right. And as you're doing that, are there some requests, a couple that we should talk about? Someone said 15 and 16? 16? Number 1D. How about the module 2, those 3 problems? Representing changes and finding average rate of change, is that okay? So, Max, are you starting today? Okay, cool. So I guess module 2 is okay. So what I heard from module 3 was 1D, 15, and 16. Any other requests from module 3 stuff? Yeah. One I. Make sure your heading's right. The heading counts for points, the folding, all that stuff. And just pass them over. Is Akalesh here? TA? Akalesh? Didn't make it. Okay, so you guys on the right, you can just stack. There he is. Here you go. They're passing him in right now. Oh, that's working. Here you go. Okay, let's take a look at some of these. So, number 1. Okay, good question. So you is a different size 10 by 13 inch sheet of cardboard? Is that right? I'm doing number 1, sorry. Number 1D. I was looking at number 2. What did I say? Number 1D. Oh, smallest possible value. Okay, so for 14 by 17 inch, we're talking about the smallest possible values of X, W, and L. Okay, that's good to talk about. So let me just, here we go. So it's 14 by 17, is that right?
Which one are you going to have
Well, kind of the convention is that length is the longer one and width is the shorter one, but you could call it the other way too, but we'll just go with that. So range for, so x is our cutout size, right? It's the side of the square cutout. So range for that. X would go from, what's the lowest possible value of x?
0.
0 is fine, okay? I know it doesn't actually make a box, but it's a legitimate value of x. We just end up with a piece of paper. Okay? Largest value of x. 7. So when we get to 7, we actually use the same cut for both the square up here and down here, and it's possible to do it. We get something like 2 7x7 squares like that. But you can't do more than that. You can't do 8. If you cut 8 here, you can't possibly cut an 8x8 square. So the most you can get is 7 for x. Okay? So therefore, when you do that, so what's the biggest length, or let's see, so what's the smallest length you would get? Well, that would be when you did those 7x7 squares. So we'd have 7 there, and we'd have 7 there, which makes 14. So then that smallest length of the box that we would get would be 3 is the smallest. 3 corresponds to an x of 7. What's the largest length we can have? 17 when x is 0. Width? So what's the smallest width we can have? 0, and we do the 7x7 cuts. And what's the biggest width? 14 when we don't cut squares. So those are the max and mins for x, L, and w. Does it make? It should make sense. It should make sense as to what's happening as you cut those squares, and when do you run out of space to cut the square. So you run out at 7x7 square, and that would be, the length would end up being 3 and the width would be 0. So these values all correspond. You get, when you have the maximum cutout, you get the minimum width and the minimum length. When you have the minimum cutout, you get the maximum width and the maximum length. Okay? Use your graph to approximate the maximum volume of the box around the nearest tenth. Explain how. Okay, so basically we're going to put that function in. Now that we have a 14x17, our length will be 17 minus a square on each end of the length, right? Length times width will be 14 minus a square on each end of the length. And what's the height of the box? Right, it's going to be whatever we cut out, that's going to be that width of that flap that we fold up, so it becomes the height of the box. So we can restrict that function to only being the x values that we talked about. What's the lowest possible value of x? Cutout length? 0.
7.
And right, we said the largest square you could cut would be 7, so that's what makes sense. So I just got to get my scale right. You have the same thing on your calculator with the, what's it called, on the window, right? So you got to make your window on your calculator correct so you can see a good view of this thing. So here's a good window for, what's our x quantity? What is this quantity on the horizontal axis?
Length of the cutout.
Length of square cutout length, right? That's right. That's this quantity down here, actually. Okay, and then what is this quantity on the vertical axis?
Volume of the box.
This is our length times width times height. That's our volume, right? So this is the volume of the box. So when we change the size of the square cutout, does the volume stay constant? No, the whole point is as we pick different size squares, we get different shaped boxes which have different volumes. So at first, as we cut bigger squares, that would represent like this, what happens to the volume as we cut bigger and bigger squares? Shoots up. But then there comes a point when we get kind of the optimum box, optimum capacity, and then after that, if we keep making the square cutout larger, what happens to the volume? Goes down, and then we know that when we get to that 7, it's just that piece of paper that we fold up like this, and then it's just 0 volume. Yeah?
A lot of the tutors at the ECA one weren't getting it because they couldn't use their graphic calculator to see.
They couldn't get the window right?
Yeah, no one could get the window right.
Okay, so like I said, we're doing our very best to train them in the curriculum, and so there will be some possibly unfortunate experiences there. So try a different time if you're not finding someone that you like. But thank you for letting me know about that. But yeah, you can't really analyze this graph unless you have a good view of it. And so to get a good view, you need the right scales on the axes. Okay, other questions? So what does it say? Really good question here. It says, find the maximum. So then once you have the good picture of it, we're looking for that cutout length, or that point on the graph. That's the highest point. So this is the ordered pair, 2.55 and 270.1, or 0.07. So what is the meaning of this ordered pair? What do those values mean? Tell the person next to you. What is the meaning of that point, or what are the meanings of those values? Go. What does the point represent? It represents a particular box, right? It represents a particular box. Which particular box does it represent?
One that has 2.55 cutouts.
So it's the one that we made by doing a 2.55 inch cutout? And the resulting volume is 270.07. This is this function that we're graphing. The input is the cutout, the output is the volume of that box. So any ordered pair will be a particular box with that cutout length and that volume. Okay? And then since I picked it very specifically as the one that's got, you can't find a box that has a higher volume than that. Yep. Yep, so this is, since all these are inches, the length is in inches, the width is in inches, the height's in inches, then that volume formula gives us inches cubed, or cubic inches. Thank you, that's important. Other questions about number 1?
Finish the question. Do the second part. Explain how you know the value you obtained is the maximum. What's the answer to that part?
So basically, by knowing that we have the correct graph, the y values of the graph are volumes. So you want the highest y value that this graph achieves, which will be at the peak of the graph. So it doesn't. What's that? It's knowing that the y value of this graph is volume, okay? And so all the y values that this graph achieves are all possible volumes of the box. So the highest y value will be, or the highest point on this graph will have the highest y value and therefore the highest volume. Other questions? Okay, let's see. What was the other? 15 and 16, was that next? Yep. Okay, so for 15, we really need to know what that function is. So what is this? What's the name of the function in number 15? What's the name of it? Remember, cost is not the name of the function. C. Remember that the little letter before the parentheses is the name. Often it's F, but it doesn't have to be F. It could be anything. It could be G, it can be, in this case, it's C. It can be anything. Sometimes they use a letter that kind of goes along with what the output is. What's inside the parentheses? In general, in the function, that's the input. And in this particular function, the input is number of gallons of milk. Okay, and so is that represented by G or anything? Okay, they never tell us. So we can put B or X or whatever we want. Okay. So then, altogether, what is C of X? Whenever you see C of X, what value or what kind of thing does that represent? Yep. So whenever you see a C of something, that is the cost in dollars of how many gallons? The way I've written it, it'll be of X gallons. So the function of this particular thing C is to take a number of gallons and give you a cost in dollars. Okay? It takes a number of gallons, gives you a cost in dollars. That's its function, right? That's its function. That's what it does. Okay? So if we have an expression like this, 2C 5 minus 1, what does that mean? So what does that whole expression represent? Yeah, tell me.
2 times the cost of producing 5 gallons minus 1.
So he said 2 times the cost of producing 5 gallons minus 1. So if we're subtracting 1 from this, what would the 1 have to mean? Dollars or gallons? Dollars, because this would have to be a number of dollars, right? Cost is dollars. Okay? So, and then they tell you that that equals some amount of money, $7.50. 2 times the cost of 5 gallons, take away $1. That's what it means. Okay? So, the last one. So, just practice. Tell the person next to you what that expression on the left means. What does that expression on the left mean? Tell the person next to you. Okay, somebody new. Somebody new. Yes, sir.
5 times the cost of producing 4.5 gallons plus 2 times the cost of producing 3 gallons is $22.20.
Did you hear him? Well said. Well said. Okay. So this is kind of in module 3. This is a big part of our journey here. Is now we're talking about how things change together, but representing it symbolically. Okay, representing it symbolically. And this function notation is the way that we represent these two quantities changing together. Yes, sir. Sure. Thank you. Okay, so here's homework number 2 coming back. Again, not alphabetized, but next time it will be, okay? So people in the front, it's going to take a while to find. Find yours, pass it on. Okay. So let's look at, are we good on number 15? Okay, how about 16? I want to do, how about 16D? D? Yeah, let's do D. So 16D talks about creating a function named g. And so we need to know, for this function g, we need to know what's it's going to be its input and what's going to be its output. All right, so it says we want a function g to express the circumference in terms of diameter. So which is which? If it's circumference in terms of diameter, so let me just give you an example. Is this x in terms of y or y in terms of x? So when we have a function and we say something in terms of something, is it going to be output in terms of input or input in terms of output? Yeah, the rule for a function is always going to give you output in terms of input. That's what the rule does. The rule is this equation or formula. The rule is the formula that's in terms of the input, and when cranked out gives you the output. That's the same thing as that, right? So that's kind of like the rule over there. It acts on the input to give you the output. So whenever you have a function and you hear in terms of, it'll always be output will be given in terms of input. All right? So it says that we want circumference in terms of diameter. So which one is input, circumference or diameter? So circumference in terms of diameter, which will be input? Diameter. Okay? And so then the output will be circumference. Okay? So then they want us to create the rule based on our knowledge of circles. Okay? So what is the rule that if we plug diameter into, it would give us the circumference? So let's just start with our circumference formula is 2 pi radius, right? And what is the diameter? Isn't 2 times r right there? Isn't that the diameter? So we could rewrite circumference as pi times d, because 2r is the diameter. So what we need is a rule that if we plug d into it, it would give us the circumference. What is that rule? Yeah, that's exactly what this is, right? Exactly what this is. So the name of this function is? G is the name. Input is? Diameter. Output? Circumference. Where in this definition is the output represented? So what part of this represents the output? That's the output, g of d. It's not a multiplication problem. That's the output of this function. It's the output when what? It's the output of g when? Which output of g is it? When the input is d. Okay, so then it says, write this expression. 3 times the circumference of a circle with a radius length of 5 units is 38. So we want to write that was part 1. G of d equals pi d. Part 2, if we're going to write 3 times the circumference of a circle, that will be 3 times what? If it's 3 times the circumference of a circle. Well, use the function notation.
3 times g of d.
It'll be 3 times g of something. Okay? 3 times g of something. Did they tell us what the diameter is? They told us the radius is 5. So I'm going to put 5 there. If I put 5 there, what does the g function think the 5 is? If I put 5 in there, it's going to interpret that 5 as diameter. That's what the g function does. Its function is to take diameter and give you circumference. So by putting a 5 there, we're not giving it what we need to give it. So the diameter, if the radius is 5, the diameter is 10. So we need to put 10 in there. And that will be for a circle of radius 5. And it says 3 times the circle of radius 5, it says is equal to 38. Three times the circumference of a circle as radius length 5/8 is 38. Yeah.
One more thing, because I just went this morning, they all said that it didn't equal.
Okay.
So they don't, is it supposed to be correct, or is it just supposed to be?
Okay, so we could take this a step further because we could find out what the circumference of this circle is, which diameter 10. That's what you did, right? You actually found that circumference and multiplied by 3, and you're saying you didn't get 38, right? Okay, so it's an untrue statement, but it's still the statement they ask us to write. So it's perfectly valid. We just note that, take it a step further and actually do that calculation. And we say, okay, that's the statement they told us to write, but it's false. It's not true. Yeah. Okay. Any more questions on the homework? Good enough. So today we're going to do a notebook check. So while we're doing notebook check, I'm going to give you some work to do. Okay, so the first thing I want you to do, I'm going to write this down. I'll just go ahead. Can I erase what's on the screen here? Are we good? Can I erase it? So we'll just do number 3. And this is on page 90, number 3. Okay? So, off limits. When you write your description. Difference. Subtraction. Minus. Etc. The point of this exercise is not to describe the operation you're doing. It's to say, okay, if you were to do that, you would get a final answer. What's the meaning of that number? Okay? So if you say it's the difference of two things, well, take it a step further. You're going to get something. What does that number mean when you take the difference? Okay? So in your description, you can't use these words, difference, subtraction, minus. We want what is the meaning of that final answer when evaluated. Okay? And then when you're done with that, I want you to move on to page 93. Okay, and I want you to go slow, and there's lots to think about here, okay? So if you race through this, I guarantee you missed it, okay? Go slow. Not only write, but also talk. So, yes, you're writing out your solutions, but then you're talking amongst yourselves and comparing, okay? So 93, there's plenty to think about there for 15 or 20 minutes, okay? So we're really practicing with this function notation. We're really practicing the meanings and being able to communicate with the function notation. That's what the goal is.